All right. Good morning, everyone. So again, if your internet is stable, you can turn on your video so we can see each other face to face on camera. Okay. So if you could do that, that would be great. Um, I think I'll get started as just a few more of you guys are still on the way here to get online, but we'll get started here. Um, I'll have, again, a couple reminders here. So second homework is due on tomorrow, okay? So just before midnight. And then again, exam one is scheduled on the week of September 14th. So about 2 weeks from now. That's my current plan for right now, but things might change until that. We'll update if there's any change. Okay, when we get close to that week. um, so over the weekend, I got a couple emails says a couple of you guys who are not permitted to come to class in person for right now. So I think for lecture wise, that's not an issue. Okay, you can just switch to online for the coming weeks also before you are permitted again to come to class. For the lab, we have to think about how we would conduct the lab in that way. So I have an idea like you can use Zoom to participate in the lab if that's the scenario. So with your partner, so your partner will be responsible for taking data, but you can join on Zoom, so you can still communicate with each other, but you'll be probably doing paperwork like entering data and then doing calculation, etc. But we'll talk about that later. Okay, I think a couple of you guys are on Friday's lecture, so things might change until Friday. So so we'll talk about it on Friday morning then, okay? And then if there's scenario coming up before Wednesday, I will address that on Wednesday morning, okay, for the Wednesday section. Um, also on the lab report, so Wednesday's lab section, you guys should have your lab finished by this afternoon, okay, or today at some point, okay. Now I mentioned in the lab sections that you can just turn in one lab report, okay. So given that uh, you guys agree, both of you guys or all of you guys agree on the answers to the multiple or the additional exercise problems, okay. Now I'll just add one more thing that if you just sometimes, I mean, rare cases, it happens that if you guys don't agree on some of the additional exercise questions, then you are fine to turn in your lab report separately. Okay, so you can do that too. Okay, it's up to you guys, but just one report is fine for me with for one group from you guys. Okay, but if you want, you can turn in your separate report as you want. Okay. So that's on the lab section here. So we'll get started, okay, with the lecture here. Let me put this in presentation mode, okay. All right. So last time we talked about free fall or falling objects, okay. So if you are near the surface of the Earth or on another planet or say on the moon, etc., then the object near the surface of this like astronomical planets or whatever you are on, you will experience some gravitational acceleration that's due to Newton's universal gravitational law. Okay, so near the surface of the Earth, okay, so this acceleration due to gravity is 9.80, okay, roughly, or the average is about this number. So we use G for that particular acceleration. So if you see G, symbol small g, that refers to gravitational acceleration, all right? And then we will use 9.8 or 9.80 in this class, unless it's otherwise specified, okay? Now, gravitational acceleration from the term, it indicates it's an acceleration. So it should be a vector scalar, okay? So it has this magnitude 9.80 meters per second square, and then it points downwards, okay? So that's always pointing downwards, okay? So that's its direction. And then from the phi equation of motion, so if you use if the object is its motion is being affected by just by gravitational acceleration g, then the phi equation of motions will be modified, because in this case, then acceleration a in those equations becomes negative g, or negative 9.80. Okay, so then you simply replace the a with minus g in all the equations that have the g in them. Okay, so but they are still the same from the same equation of motion. Okay, so last time we were on this one here, we were about to check on the solutions on this one. So many of you guys have submit your answers to this problem, and then some of you guys got the answer right, but we'll take a look here together today. Okay, so I'll just try jump right on the solution here. So let me stop sharing my screen. Okay, so if you could pull up the PowerPoint slide on your end, that will help. Okay, so it's the sixth lecture. So that means you can type in tinyurl.com/PHY2014-06. Okay, but we'll take a look here. Let me switch my camera on the piece of paper on my table here, so you can see my work here. All right. So this one says a lava, the lava bomb being shoot up from the summit of the volcano. So a geologist observing the eruption of the volcano use a stopwatch to time the flight, okay, of the lava bomb. So when it leaves the summit and then return to the summit, it takes 4.75 seconds, okay, and so the first, so the physical principle here should be the one-dimensional motion, right? And then because this one, the motion of the object is only being affected by gravitational acceleration, so then A will be equal to G, okay? So it indicates that we are going to choose the upward to be the positive direction, okay? So let's put that way. And then it uses y coordinate instead of x coordinate. Okay, so that would only change the equations, the phi equation of motion, where the x, you can replace x with y. Okay, so this is your coordinate system. We know that, so if you pick the summit of the volcano to be the origin, then that's 0. Okay, so that indicate that your initial y is 0, right? Your position in y initially should be 0. Now it takes the time it takes, it goes up and then comes back down. Okay, so in that way. Now when you return to the summit, so the final position then it's also 0. Okay, so this is not indicate or it's not state in the problem, but it actually you can infer this information, okay, by examining the problem here. So this is critical here as well. All right, now the time it takes t is equal to 4.75. Now, because you pick upward to be the positive direction, so then acceleration is equal to minus 9.80 meters per second square, okay? Because acceleration is pointing downwards, so it's negative because you pick upward to be positive direction. So then we have those pieces of information as knowns. Now let's take a look. It's asking what's the initial speed, okay, of v0. So part A is asking what's v0. All right. Now we can relist the phi equation of motions. So the first one, let's see. The first one, it says x equal to x naught. So I'm going to replace x with y. So y equals to y naught plus v average times t. Okay. The second one, it says v average is equal to 1/2 of v final plus v0. The third one says y is equal to, or x is equal to, but I'm replacing x with y. Okay. y0 let me see. I actually kind of, let me find the equation of motions. So as you can see, I don't remember all of them, but so you guys, it's also fine for you guys not to remember all of them, okay? But you can always look it up, okay? So the third one says, actually, the third one says velocity. Velocity equal to initial velocity plus AT. So our A is minus G, so minus GT, okay? The fourth one says X, I'm writing Y here because we are using Y is equal to X0 plus V0 T, okay? Now again, plus 1/2 AT means minus 1/2 GT square, okay? The last equation says V square equal to V0 square plus or minus, in this case, minus 2G. Now Y minus Y0, okay? So these are now the equation of motions, okay? So we are looking for V0, okay? You kind of check the equations you have. So you might be, so the first one doesn't have V0, okay? So we probably don't want to start with that one. The second one has V0, but the problem is we don't know the V or V average here in this scenario, okay? So one equation has two unknowns, then you cannot solve for the V0, okay? Now let's get the third one here. If you check on the third one here, again, we don't know the V final yet, although you know G, no T, but this is also an unknown, the initial velocity, okay, speed. So you couldn't solve for the V0 from the third one here either. So continue looking on the fourth equation here. So this one has, it's pretty, a longer equation here, but it looks like we have the T, we have G, we have Y and Y0. So the only unknown here is the V naught we are looking for, okay? So if you check on this equation, and then you will figure that, okay, so it looks like V naught is the only unknown in this equation. So I can use this one, okay, to solve for my V naught. So I'm going to just use that one, pick that one. So my Y is equal to 0. My Y initial is 0. So I'm going to just plug in the numbers. So, okay, Y equal to 0 is equal to Y naught plus V naught times the time 4.75 second. Okay, minus 1/2 G is the 9.80 meters per second square times T square 4.75 seconds square. Okay, so then you can solve for this guy. All right. Now you can calculate this term first for right now, or you can leave it. So it's up to you, whichever you think you feel, whichever way you think you feel comfortable solving this problem. Okay, I'm going to keep this one here, or actually I will just divide every term here by 4.75, because if you divide everything by 4.75, okay, then the equation still stands. Okay, if I do that, so this is still as 0 equals to 0, I'm going to just leave it out. So this term divided by 4.75, so goes away. So 0 equals to V0 minus 1/2 9.80 meters per second square. Okay, so I have 4.75 square on top here divided by this guy, so I get rid of the square, but I still have 4.75 second remaining down there. Okay, so now it tells me V0 minus this thing becomes 0. So I can calculate about this one into my calculator now. So it will tell me this is going to be 23.275 meters per second on this one. Okay, so my V0 minus this guy equals to 0. That tells me my V0 is 23.275 meters per second. Okay, if you just keep 3 digits here, 23.3 meters per second. Okay, and then quite a few guys got this one right. All right. So and then some of you guys got like 46 something, so you probably forgot about the 1/2 turn along the way. Okay, probably forgetting that 1/2 factor there. Okay, but this is part A. Okay, let me know if you guys have questions on this one. Okay, you can unmute yourself. I think I mute all of you guys, but you can unmute yourself and then speak up for question. Okay. All right. So if you are all clear on this one, then we are going to look at the part B of this problem. It asks you, how high above its launch height does the lava bomb go before its velocity turns direction? Okay, so we want to examine the motion of the lava bomb. So it goes up with an initial velocity, all right? Now, because the gravitational acceleration is pulling it downward, so your acceleration is going downward here. So then this velocity will decrease, or the speed will decrease, right? So then become smaller and smaller. And then when it reaches the highest point, okay, so then over that at that point, the velocity at that instant will become 0, right? And then it turns direction and then increase its speed downward, right? So that's the motion of the lava bomb if you examine the scenario here. So that's what's happening here because the acceleration is pulling it downward. So then this one is asking you, what's the height? How high above this initial height? Okay, so that means you're looking for this y here. Okay, from here to the initial launch point. Okay. Now this is a different y. Okay, so this is in part B, the y in part B. Okay, in part A, the final y is here. So these two are different. Okay, this is not 0 anymore. Okay, so just want to point out that although we are using the same notation in the two parts, but they are referring to different height. Okay. All right. Now, in this part, now from A, we already know that the initial speed. Okay, so now this one becomes known. Okay, so 23.275 meters per second. All right, and then in addition, the knowns in the previous part, these ones, those three pieces should, this and this should still stay. Okay, and the t will be a different t. Okay, it's not at the same position right now, but y0 should be still 0. A should be minus 9.8 meters per second square. Okay, so now we have those three pieces as the known information. We are looking for y. Okay, so and then one more thing here, v final is 0. Okay, so because at the high point your velocity should become 0 momentarily before it turns direction. Okay, so we still have four pieces of information but slightly different. Okay. Now we are looking for y. That's all we are looking for. So we still will be looking at the 5 equations of motions, okay, in the as I list them over here on the first part here. So you can see we are looking for y here, all right? Y naught is known. V average, all right, this is unknown. But there's a way to figure it out because you know V final, you know V initial. So this can be figured out, okay? So it's half of final plus initial divided by 2. You can figure this guy out, all right? But the T is not known. The T given in the problem, it refers to when the lava returns to its initial summit, the initial height, the summit, okay, not the high point, okay? So then P is unknown in the second part. So you couldn't use the first equation to figure out your Y directly. The second one, you can use it to figure out your average V, okay? But it doesn't help to solve for Y. The third one here doesn't have Y in it, so you will probably not refer to that one. The fourth one here has Y, and it has Y0 is the known, okay? V0 is the known, it's the 23.3 we solved, all right? But T is an unknown, okay? We don't know the T yet, all right? So we probably cannot use this one as well. Now the last equation here, you can see final V is known, initial V is known, okay? Y or G is known, Y0 is known. So only Y is the unknown in the last equation, okay? So in this case, then you'll be using the last equation, okay, in part B to solve for your Y, all right? So let's take the last equation down here on part B, V squared equal to V0 squared minus 2G Y minus Y0, okay? Now looking at the knowns here, I know that my initial Y0 is 0, so that term goes away, okay? Now V final is 0, so this term on the left also goes away. The 0 square is still 0, okay? So then I can simplify this equation. So on the left is 0 equals to V initial square minus 2GY. And then I'm looking for Y, okay? So this guy minus this guy equal to 0. That tells me that V0 squared then is equal to 2G times Y, okay? So then if I divide both sides by 2G, I will get rid of the 2G here. And then I have only Y remaining on the right, okay? So then I can solve for my Y. So my Y is going to be equal to V naught square over 2G, okay? Which V0 square is 23.275. I'm going to just keep the original all digits here, okay? 2 multiplied by G, okay? So then it tells me this is 27.639 meters, or keep 3 digits, 27.6 meters. Okay, so I also saw some of you guys got this one right. Okay, so that's great. Okay. All right. Questions you guys might have on this one? You can unmute yourself and speak, okay?
Yeah, I got a question.
Go ahead.
Okay, so when the acceleration changes from 9.8 to just positive, when it goes from like, why did you change a negative to the positive?
So okay, so here's the thing. Okay, so when you see G, that is always, so G is always just 9.80. Okay, it's the magnitude of the oscillation. All right, so this guy is always positive if you just indicate this is the magnitude of it. Okay, so initially when we say because this is minus G because oscillation is negative G, right? So this is clear on the equation, this is negative, okay? But in the second part here, if you look at the algebra here, this is minus 2G times Y, right? But I didn't change it to negative intentionally. This is just because algebra, okay? So if you move this thing to the other side of the equation, negative becomes positive, okay? This is just because algebra, all right? Is that what you refer to when I change the oscillation from negative to positive?
Yeah.
Okay, yeah. So that's just due to algebra. It's not like I change it intentionally over there, okay?
Okay.
Yeah.
Thanks.
Okay, great. All right. Now okay, yeah, you asked that in the chat as well, so that's been taken care of. Okay, so let's look at another aspect of this. So as I put this in the note, at the highest point of the flight, the speed of the bond reaches 0. Okay, so when you have a free fall problem, if the object reaches the highest point, vertically, then its vertical velocity will be 0, or vertical speed will be 0. Okay. When we talk about two-dimensional motion, we'll talk about that as well. Okay. But now another point about if you are throwing an object up. Okay. So let's see. We have figured out what's the height, how high it goes. Okay. Vertically. Now, how much time does it take? Let's take a look. Okay. Let me share the PowerPoint again with you guys. Oh, actually, let's do it on the paper here again. Okay. So, how do I figure out what time it takes here? Now I have my y here. Okay. If I want to solve for my time t, so then I would look at the equations, skim through all the equations. I figure like this one has t, the fourth one has t. So I probably will go either the first one or the fourth one to solve for t if I'm interested on the time it takes to reach the highest point. Okay. So again, on this one, I wouldn't have V average, so I probably wouldn't use the first one. But the fourth one, let's take a look to see if we have all the information needed to solve for T. I have Y now solved. I have initial Y, I have initial V, I have G, so I can solve for the T. Okay, so if you want to solve for your T, you use the fourth equation now. Y equals to Y0 plus V0 T minus 1/2 GT square. Okay, so again, y0 is 0 here. Okay, or I can keep it. Yeah, it's 0. I can take it out. Okay, and for y, it's going to be this number, right? But we got this number from this expression, so I'm going to just keep the expression in the place of y here, doing some substitution here. Okay, so then I will have y0 squared divided by 2g on the right equals to v0 t minus 1/2 g t squared. Okay. Then I can solve for the t from this equation. Okay. So if you want to solve for t here, it's going to be a quadratic equation, but I'm going to multiply both sides by 2g. Okay, so 2g multiplied by this side, and then this side will be also multiplied by 2g. So I get rid of the 2g on the left. Okay, so then v0 square equals to vt times 2g minus, okay, the 2 and 1/2 will cancel out, but g and g will multiply. Okay, so gt square. All right. So then it will be a quadratic equation. It will tell you this is going to be minus g squared t squared plus 2g v0 times t. Okay. And from the right hand side, I will move this guy to the right. So minus v0 squared equal to 0. All right. Now I can solve for the quadratic equation here. So the solution for this quadratic formula for t is going to be equal to t equals to, so minus b, this is my b, for a quadruple equation ax squared plus bx plus c equal to 0, okay, formula. Now in this case, your a is minus g square, your b is, this is your b. So this is your a, this is your b, this is your c. Okay, so minus cb means minus 2g v0 plus minus square root of 2g v0 square or minus, okay, b square minus 4c 4 times 4ac, okay, 4 minus g square and then minus v square. Or rather, I think it's plus b square plus 4ac, okay, divided by 2a minus 2g square, okay. So let me see if I get everything correct here. Oh, wait a second. This might be too complicated here. Right, I think, yeah. So it might be too complicated here. Let me switch to another way. Okay, so we should be able to do this in an easier way here. So again, look at the 5 equations we have here. So because we are looking for t, right? Now we can figure out this guy actually because we have solved for the final v, we have the initial v, okay? Which is the final is 0, initial we solved. So we can use this one. Then we can actually take this v here into the first equation to solve for t, which will be more easier instead of solving the quadratic equation, okay? So let me do this. So let me solve for v average here as 1/2 of the final, which is 0, plus the initial 23.3, or roughly 275 meters per second. Okay, so this is roughly 11.63 or 4. Okay, let me just keep 11.64 meters per second for this guy. Now, in the first equation, it says y equal to y0 plus this average times t. So then y, we have solved it to be 27.639 meters, right? Equal to initial y0 is 0 plus this 11.64 meters per second times this t, right? So we can solve for this guy easily, other than what I just show you the quadruple equation. So okay, so then everything divide. So this is 0 that go away. So everything divided by 11.64 on the right, also 11.64 on the left will give you my time t, right? So then this would be turn out to be 2.375 seconds, okay, equals to t. All right. So I think this way that's much easier to show you how to get the time t. All right. Now, if you look at the time t here, so this is when it reaches at the high point, okay, t of high. So let me just do a subscript here, say indicating this is at the time it takes to reach to the high point, okay? Now compared to the total t or t subtotal, 4.75 second initially, okay? So you see that the t high is equal to, actually, this is exactly half of this guy, okay? So it's actually exactly half of the t total, okay? So that means the time it takes for the object to go from the initial launch point to the highest point should be equal to half of the time for when it gets back to the original position, okay? So it takes the same time to go up and then the same time to go down, okay? So t up and then t down, they are equal to each other, okay? So t goes up is equal to t goes down. Okay, so these two are the same. Takes equal amount of time. Okay. So if you figure that out, okay, so then so this is one piece of information you might use later on for similar problems. Okay, it will take about the same time to go up and goes down when if the initial and final position are at the same height. Okay. Also for the final speed, if I'm looking for the final speed, okay, I will use the third equation from the equation of motion here. So I will use the third equation. So this equation to figure out my final speed when it goes back to the launch point. Okay, so I can figure out what's the final speed at this point as well. Okay, so if you want to check that, you use this equation, then you can see that V final is equal to V initial minus GT, okay, equals to, now this is the total T because I'm referring to when it goes back to the original position, 23.275 meters per second minus 9.80 times 4.75. Okay, this is meters per second squared, this is in second. So I will get minus 23.275 meters per second for the final speed, okay, when it returns to the original height. So you'll see that this is exactly the same magnitude as the initial speed of 23.275, okay? This is equal to V0, all right? So when the object returns at its initial height, it actually will have the same speed, but just in the opposite direction, okay? The direction is negative, all right? But this is positive initially going up, okay? So when the object being thrown up, and then when it comes down to the original position, then this speed should be the same, but direction of the velocities are different. Initial velocity is going up, final velocity is going down, okay? So these are two additional points for an object that is experiencing just gravitational oscillation for its motion, okay? So two additional points. I can add this later on the PowerPoint slides, or I can do it right now, okay? So let me go back to the PowerPoint slides here. So this is what we discovered earlier. So at the highest of its flight, the speed reaches 0, okay, before it turns direction. All right, let me see if I can just add it right now. And then when it returns to the original height, the speed is the same, but velocity is pointing downward. Okay, so this is another thing here. And then another piece of information about an object that is being thrown up is it takes the same time to reach the high point as it goes back down from the high point, okay? Or simply saying it takes half of the time to go up, reaches the high point, and then the second half to go back down to its initial positions, okay? So these are three pieces of information we can learn from an object that's been thrown directly upward, okay, and then coming down to its initial position, all right? Questions you guys might have? So if not, let's move on here. All right, so the next section in the textbook talks about graphical analysis of one-dimensional motion. We kind of touched on this earlier last week, but we'll take a closer look again, okay? So to start with, this is a quick review of the algebra or math here. So if you have a 2D like XY coordinate system here, you have a curve which is in red here. So if this is a linear here, then you can express the Y in terms of X in this fashion, Y equals to M times X plus B, where X is the independent variable and then Y is the dependent variable, okay? M and B are the two constant numbers or two parameters, which M is the slope of the line and then B is the y-intercept of this line, okay? So to find out the slope, then you use the rise over run. So delta y over delta x, that gives you m. Okay, so you simply pick any 2 points from the curve, from the line here, then you do that difference in y divided by difference in x. Okay, it'll give you the slope. All right. So because of that, and then the velocity is defined as delta x over delta t, right? So then if you have a x displacement versus t plot or graph, then the slope between any 2 points, it'll be the velocity, right? Because then the slope is the same as the definition of the velocity. So then that gives you the velocity, okay? I'm going through this quickly because we have kind of talked about this earlier last week, okay? When you have a linear, or if you have a constant acceleration motion, then this is a displacement versus time t curve. Okay, it's kind of looks like half of the hyperbola curve. Okay, so go upward. Okay, so then this x on the vertical axis is equal to x naught plus v naught times t plus 1/2 at squared. You can see this is quadratic equation. Okay, so then this is a hyperbola curve. Okay, now our t starting from 0, so you're having this just 1/2 of it. Okay, so on this one here, if you take slope at any points, then you'll get the velocity at that between any 2 points. Okay, so then you'll get the velocity of it. Then you can plot your velocity on a second graph, like velocity versus time t, out of this guy. Okay, if you do that, you'll figure out then velocity versus time will be a linear function. All right. Now, because this is line, you can take a slope of this linear line here. You'll figure that the acceleration, because then similar to velocity definition, acceleration is equal to delta v, change in velocity over change in time t. So then if you have velocity versus time t graph, the slope of that graph will be the corresponding to the acceleration, okay? So then you'll get the third graph here, which indicate the acceleration is then uh, a constant acceleration because it's phi all the time. Okay. Now, in the lab, one of the labs you'll be recording the x position. All right. It's still a few weeks from now. Okay, you'll be doing the lab, the free fall lab. You'll be recording the object's position versus time t, and then from there you are going to measure, or you are going to study the so basically you are having a plot graph of this one, the first one, and then from the first one you're going to determine the velocity versus time t, and then the acceleration. Okay, so this is one way of figuring out the acceleration. Okay, let's take one example here. Okay, so if you are given a distance versus time t graph, all right, so then this is distance versus t. All right, it's asking you A, when is the car moving the fastest? And then B, when is it moving the slowest? And then when is the car not moving at all? Okay, so, and then D, at what time does the car start moving in the opposite direction? Okay, so I will have you guys answer these four questions here. You see in C it says when is the car not moving at all. So let's make a difference between when the car is not moving at all from when it's moving at slowest. Okay, so let's take a note here. In part B, when it's asking when it's moving the slowest. Okay, so some people may say, okay, when it's not moving, that means it's moving at slowest. Okay, so but let's just put this in the case of when it's actually moving. Okay, and then referring to when it's moving slowest. Okay, so it's actually moving but moving slowest. Okay, on the second question here. Okay, you can click on any of this one. They are having the same link. Okay, and then you can answer that question. So I'll give you guys about 2 minutes on this one. I think it will be easy on this one here, and then we can check on the solution together. Okay, in about 2 minutes. All right, I've seen some of responses from you guys already. You guys can keep submitting your answers if you haven't done so. Okay, but let me just get started. Okay, on this one. So the graph here shows distance versus time t. Okay, and then it's asking you about how car is moving, how fast or slow it's moving. So it looks like the questions are related to the velocity or the speed of the car. Okay, so we can figure out there are there are four parts of the motion here. Let's see, okay. So the first part is from 0 to let's see, from 0 to 20 seconds. Okay, so 0 to 20 seconds. Then let's see what would be the speed or velocity of it. Okay, so we'll be doing delta x over delta t over that time interval. Okay. So let me see, out of focus. Okay, looks better now. So delta x here, it looks like about say from 0 to a little bit over 15. Okay, so a little bit over 15. So I'm not sure what number is that, but it looks like that maybe 16 over time t20. Okay, so that's the first part of velocity. Second part from 20 to 30 seconds. Okay, so V2 then will be equal to delta x. This is x1 over delta t1, delta x2 over delta t2. Okay, so then in this case, the distance or the position of the object actually doesn't change. So the change should be 0 divided by the 10 seconds. Okay, so that should be 0. The third part, it goes from the 30 seconds to 50 seconds. Okay, so it looks like it's at about 25, the final as the final. Okay, so maybe 25 minus whatever 16 or 15 divided by the 20 seconds. Okay, will be 29 on the top. Okay, 20 on the bottom here. The last one from 60 to 50 to 60 seconds. Okay, so V4 here, you can kind of see that on this one, it goes from about 25. So delta x actually start from 25. So minus 25 goes to about, yeah, hard to tell. Maybe roughly maybe 18 or something. Okay, divide by 20. Okay, so then negative or 20 over 7. Okay, so in this scenario, okay, I think I'm doing just the best estimation that I can read from the graph. Okay, so you already might be a little bit off, like say here you may be reading like 19 or 17, whatever. From here it may be reading 17 or 15. Okay, but doesn't really matter too much. Okay, so then you can see part A or question A is asking you when is the car moving fastest. Okay, so it looks like this one is the fastest. Okay, so A will be from 0 to 20 seconds. Okay, and then B when it's moving slowest. Okay, so it will be, it looks like this one. It's the 7 over 20. Okay, that's the slowest. Okay, or maybe because my reading is not off, so it could be these two actually are the same. Okay, so if you either answer with 30 over 50 seconds or 50 to 60 seconds, okay, I think that's fine. Okay, but for a real or actually real problem in the test, I should have make this clear of what will be the final and initial on each part. Okay, on C here, when the car is not moving at all, that means so the velocity is 0. So it will be this guy from 20 seconds to 30 seconds. Okay. D, at what time does the car start moving in the opposite direction? So when it changes direction, it changes the sign. Okay. So from positive, so this is positive and 0. 0, it doesn't change, it just stops. Okay. And then positive and then negative. So after that, it's negative. So it's starting from the 50 seconds. Okay. So this should be the answers for this one. Okay. Any questions you guys might have? If not, then we'll look at the last slides here. Let me reshare my screen here. So again, it's a graphical representation. Um, it's asking you in the graph shown is the velocity constant for any time interval. Okay, so this time you have v versus t. Okay, so then you're looking for oscillation. So again, you'll be looking for the slope of the curve at any time interval. Okay. It's asking you if the velocity is constant for any time interval. So, oh, actually, yeah, it's not asking for oscillation. Sorry, my apologies. It's asking for the velocity. So you can just read straightforward from the graph. Okay. All right. So many of you guys have submitted your responses. We'll take a look here. So it's asking for when the velocity is constant. That means the velocity doesn't change, okay? So from the plot, it's clear that from 0 to 2 seconds, that velocity doesn't change because it's a straight line. Now, this is a velocity versus time t graph, okay? So you are looking for velocity, then just read from there. So some of you guys says it's from 2 to 4 seconds, but most of you guys says from 0 to 2, okay? So from 2 to 4 seconds, actually it maintains constant oscillation. It's a linear on the VT graph. That means it's constant oscillation, okay? So that means the oscillation is not changing. From 4 to 8, again, it's a linear, so the oscillation between those two time instant that shouldn't be changing. So from 4 to 8, it's also constant oscillation, okay? Yeah, so on this one, the correct answer should be A, okay? All right. I have just about a couple minutes left here. Any one of you guys have any questions on homework number 2? So I see many of you guys have started working on number 2, but still a couple of you haven't started. So if you haven't, it's good for you to start it today, okay, at some point, because if you wait until tomorrow, you wouldn't have probably wouldn't have enough time to finish them all, okay? But any of you guys have questions on any of the homework problems? Let's see. think. All right, so there's a question in the chat going asking two cars meet problem. So I think, let me see, and that's now if you don't have a problem, questions on homework problems, you can leave. Okay, so you don't have to stick online from this point on, but you can leave. But let me see. So the two cars meet problem, I think that's number 6. Let's see. Right, is that correct? Number 6. All right. So number 6. If you have two car meets each other, now each one has different acceleration. Okay, so you can sketch the problem. You can say this is your axis. Now you have car A starting from here somewhere. You can sketch your car A. Okay, and then you have a car B. Let's see, something like that. So this one has, now on my end, it says 11 meters per second square. You probably have a different number, okay? So this is my acceleration of A. And then on my end, it says my acceleration of B, this is minus 7 meters per second square. So that means it's going in the opposite direction, okay? So if positive is to the right, okay? So then it indicates those two. It says the cars are initial at rest and separated by a distance of 3,800 meters. Okay, so this is the whole distance is 3,800 meters. On my end, you might have a different number. Okay, so it's asking you at what time do the two cars meet. Okay, so then both of them are having one-dimensional motion, right? So you can see they will meet at some point, say here. So then on this one, on car 1, car A is going to travel distance dA. On car B is going to travel distance dB. Okay. So then the distance dA, that should be equal to, in this case, you can see dA is going to be equal to, if this is XA naught, initial position XA naught, then this is XA final, okay? If this is XB naught, this is XB final. Okay, so you can see XB should be the same, all right? Now, for your XA, you can check on the 5 equations of motions, okay? So it tells you the initial VA0 is 0, VB0 is 0. Both of the two cars has initial velocities of 0, okay? So you can use that equation. XA should be equal to XA naught plus VA naught times T plus 1/2 A of AT square, okay? And then XB, similarly, you can use this equation. Now this is to pick one of the 5 equations, okay? So I'm not going to just list all of them, but this will be the one I pick, okay? The fourth one. Apply this fourth one equation to B as well, VB0 times T plus 1/2 AB T square, okay? So you have 2 equations. Now it says both cars initially at rest. So that means this term will be 0, and then this term will be 0 as well, okay? So then, because they meet at this point, okay, so XA and XB, they are the same, right? It's the same position in the middle, right? The final of A and the final of B should be the same, right? So XA should be equal to XB. XA should be equal to XB, okay? That means you can set this guy equals to this guy, okay? If this equal to that, that means this equal to that, right? So you can say XA naught plus 1/2 AA T squared is equal to XB naught plus 1/2 AB T squared, okay? So then now we are looking for T, right? We can move the terms with T to one side of the equation, and then leave the rest of the terms on the other side of the equation. Okay, I'm going to move this guy to the left and then this guy to the right. So then I will have 1/2 AT t squared minus 1/2 AB t squared equals to XB initial minus XA initial, right? Now you can see on the left here, you have both T's. You would like to separate T's from the other terms. Okay, so that means you're going to do 1/2 A minus 1/2 A of B times T squared, right? You are solving for T, so you want to single out the T, okay? XB naught minus XA naught. All right. Now you can see if you have XB naught minus XA naught, this is your original separation of the two, right? The distance between the original positions of the two cars will be the distance of the separation of the original cars, right? So it will be let D. In my case, it will be 3,800 meters, okay? That will be, so this is D, this guy. XB naught minus XA naught, this is D, okay? So then in my case, I can plug in my numbers here, 1/2 times 11 minus 1/2 times minus 7 times T squared is going to equal to my 3,800, okay? So then I can solve for the T, okay? Because T is the only unknown here, all right? Now remember, because you are solving for T squared, so it'll give you a positive and a negative number. You will drop the negative number because time couldn't be negative, okay? So this is part A. And then you can solve for part B if you know the T, right? You're looking for displacement. You'll be doing, you pick one of the equations that has X and then solve for that one. I think you might have a question on part D. If the two are originally not as having initial 0, okay? So then in that case, again, you'll be doing the same, but just instead, this guy is not 0, this guy is not 0, okay? It's just plugging the numbers that original numbers of these two, okay? Then you'll have extra terms with T, all right? You'll set, again, this equal to that, so then this side equal to this side, again, without these two being zeros, okay? But then in that case, you'll be solving for a quadratic formula instead of just doing T squared, okay? But you guys should be able to, or you guys can try it, okay? To try to solve for the quadratic equation, all right? And then again, you'll get two T's, one being negative, one being positive. You'll drop off the negative one, okay? To just keep the positive number, okay? And let me know if you have questions on any of these steps. Let me see, there's a chat here. All right, so if you guys, now problem 10 on the last part is about this. You also have to solve for quadratic formula, okay, on the last one. So these are the two questions that will require you to solve for a quadratic formula, okay, in a similar fashion as we involving the t squares, okay, if you get to that point. All right, so for tomorrow or today afternoon, I should still have time for virtual office hour, okay? So if you have question, you can let me know you want to discuss anything on the Zoom, okay? So other than that, think we'll just stop here for today, okay? All right, see you guys on Wednesday. Bye.